Science and Education and Research at Kolkata, and he is going to talk about the Darboux Theorem.
Okay, so I thank the organizers for the invitation. So in this lecture, we'll be talking on the Darboux type theorem. So this arises in the context of pullback equation. So these equations arise in the study of differential forms very naturally. So we begin with the definition of pullback. So in simple terms, pullback refers to the following. So we have a function f of variable y, where y itself is a function of another variable x. Then one can write f as some function g of x. And we say that g is a pullback of f via the function y of x. So more generally and formally, we define pullback in the following way in the context of differential forms. So let n stand for the dimension of the space, and k is an integer that will stand for the order of the differential form, and omega 1, omega 2 are two open sets, and let g be a smooth differential k form, which we write in the standard way. G is summation over gi dxi, and I is in tk, where tk is a set of all strictly increasing k tuples, and gi is a smooth function defined over omega 2, and dxi is the wedge product of dx of ia1 up to dx of ik. When we define the pullback of g via a function, smooth function, that is C infinity function from omega and omega 2, is as a differential form, which we denote by phi star g, that is defined on omega 1, as opposed to g, which is defined on omega 2 as phi star g is the gi composed with phi times d phi I. Okay, so let us look at some examples of pullback. So when k is equal to 0, pullback is essentially the composition of function. So this is the example that we started the lecture with. And when k is equal to 1, phi star g is a quasi-linear operator, that it's linear with respect to the gradient of phi. And when k is equal to 2, it becomes completely nonlinear. Note that it involves now 2 by 2 minors of the gradient of phi. And it's a homogeneous polynomial of degree 2 of gradient of phi. In general, for k form, a pullback is a homogeneous polynomial of order k of gradient of phi. Finally, when k is equal to n, the pullback of g is g composed with phi multiplied by the Jacobian determinant of phi times the standard volume form. Okay, so with the definition of pullback in hand, we ask the following question. Suppose there are two differential forms defined over a domain. We ask that when is one form is a pullback of the other via some diffeomorphism. So in general, so what we ask the following question, given two forms f, g that are defined on omega, does there exist a diffeomorphism of the domain omega such that phi star g is equal to f in omega? Now if there exists such a diffeomorphism, we say that f, g are equivalent. So geometrically, all that it means that f, g are identical up to a change of coordinate. Now note that for any f, g, we cannot expect to have a diffeomorphism that satisfies this relation. Now this can easily be seen in the context of zero form. Say one form is a constant zero form, one is a constant function, whereas the other is not, then one cannot expect to have a diffeomorphism satisfying the pullback equation. Therefore, it is natural to ask under which conditions there exists a diffeomorphism that satisfies this relation. It is also natural to ask when two differential forms are locally equivalent. We say two forms are equivalent if one is a pullback of the other. Now the question is, when two differential forms are locally equivalent, this means that given any point of the open set, does there exist a neighborhood on which we have a diffeomorphism such that this equation is satisfied on the neighborhood? It is also natural to ask if there exists a diffeomorphism which, in addition to satisfying this relation, satisfies a boundary condition as well. And one issue that is particularly very important to us is what can we say about the regularity of the diffeomorphism? See, note that this is a system. This is a system of the first order equation because this system involves the first derivatives of phi. Therefore, it is natural to ask, do we have a solution that is one order smoother than what f, g are? So these are the questions that we deal with in this equation. Okay. Now, before we get to our work, so we will look at some earlier developments. Okay, this is something that is can be said. So this is a basically we can see a pullback as a change of variable formula for the differential forms. And okay, now locally for the case of closed non-degenerate 2 form in even dimension, this problem was first solved by Darboux in 1882 when he proved that in even dimensions any closed non-degenerate 2 form is locally equivalent to the standard symplectic form. Okay, now see that. So by locally equivalent again we mean that given any point we have a neighborhood on which we can find a diffeomorphism that is defined on the neighborhood such that the pullback equation is satisfied on the neighborhood. Okay, so what about a global situation? So what can I say? Now this is a local, what Darboux solved is a local problem, but we are interested in the global situation. Now we start with the simplest case. Okay, so let us assume that A, F, G are now constant 2 forms. Okay, now this is then it's a simple exercise of linear algebra that any non-degenerate constant 2 form is the globally a pullback of the standard symplectic form by a linear isomorphism. But that's really the easy case. We are interested in the non-constant case and the global problem. In the global scale, without the boundary condition and the question of sharp regularity, this problem for the closed form was first solved by Moser for the case when k is equal to 2 when n is even and k is equal to n. Now to solve that problem, Moser introduced a famous method now known as Moser's flow method, where he considered the flow associated with a vector field ut as follows. So ddt of phi t is equal to ut phi t and phi 0x is equal to x, when a solution of the pullback equation is given by phi is equal to phi 1. Therefore, the question that arises at this point is how do we construct the vector field ut? Now, this vector field ut is recovered by 2 fundamental equations which we refer as a constituent equation. Now, let us see what does the equations look like. First thing is d alpha t is equal to minus ddt of ht, where ht is a closed non-degenerate homotopy between f and g, and then is iut ht is equal to alpha t, where iut is the interior product which is defined as basically it maps a k form to a k minus 1 form. So H is a closed non-degenerate homotopy joining f and g, and iut is the interior product and the contraction operator. Now once we have the vector field ut that satisfies these 2 equations, it is easy to check that phi is equal to phi 1 does indeed solve the pullback equation. And how do we do that? See, the one way to do it, it's obvious that, now one way to proving this is, if we show that phi t star ht is independent of t, then we are done. Because if phi t star ht is independent of t, then this implies that phi 1 star h1 is equal to phi 0 star h0. But you see that phi 0 is the identity function, and h0 is the homotopy. So once I show that phi t star ht is independent of t, we are really done. And how do you show that phi t star ht is independent of t? We differentiate. Once we differentiate with respect to t, then we using the Lie derivative formula and this famous formula due to Cartan, and the constitutive equation shows that phi t star ht is indeed independent of t because the derivative is 0. So now since it's a routine calculation, we will not do it here. This calculation can be found in any differential geometry book. So we'll skip the calculation here. Therefore, the question that arises at this point is, how do we solve these 2 constituent equations? You know that the first equation is at least locally solvable. Why? Because of the Poincare lemma. Because ht is a closed form, therefore we can solve it locally. So what about the second equation? Now Moser observed that it is well posed in the sense that no matter what alpha te is, there exists a unique ut solving this equation only when k is equal to 2 when n is even, or k is equal to n. For example, let us consider the case of positive volume forms. For example, let us consider the case of positive volume forms. So if g are positive, therefore the obvious homotopy we take the linear homotopy. Tg is equal to 1 minus Tf. Okay? So if we take the homotopy as then let us look at the constituent equation. So ht, then ddt of ht is independent of t. It's f minus g. So alpha doesn't depend on t. Now what is this second equation? The second equation is essentially the product. So ut is equal to alpha by tg plus 1 minus tf. So one can solve it for the case of volume forms. Of course, this method does not work when if the volume form changes sign, and yeah. So that's how one does. Now, after the 1965 paper of Moser, the case k is equal to n received considerable attention by many, most notably by Riemann, Boniaga, Zender, Tartar, de Coronia. Now, it is important to note at this point that until then the question of sharp regularity and the boundary value problem were not considered. The case k is equal to n, that is the case of volume forms together with the boundary value problem, and the question of sharp regularity were first addressed by de Coronia and Moser in 1990. Now, it is important to keep in mind at this point that the Moses flow method, however powerful and elegant it is, it does not allow us to handle regularity problem, because it produces a solution that is just as regular as what f and g are. Where this being a first order equation, we are expecting whether there exists a solution that is smoother than f and g. Now, this drawback of Moses flow method was negotiated by combining the flow method with an iterative scheme to arrive at the following sharp regularity result due to the Coronia and Moser. So let omega be a bounded and smooth domain. Now, for domain for us is open connected. And m, let m stand for the degree of regularity, alpha be the Holder exponent, and fg are two positive volume forms. Then there exists a diffeomorphism of class Cm plus 1 alpha that satisfies the pullback equation together with phi is equal to identity on the boundary if and only if the integrals are equal. The necessity of this condition is quite obvious because it's nothing but the change of variable formula. What is non-trivial is a sufficiency. Okay. Now, after this result of the Coronia and Moser were extended to various other function spaces by, for example, EA in 1994, who extended to sublab spaces, higher order sublab spaces. You note that a higher order means AMP greater than n, so the sublab space becomes an algebra there. And then Riviere, who did it for on the continuous space, BMO and L infinity. So, okay, we skip the results for this time being, it's not going to be important in this talk. Okay. So, you see, the thing is, so the case of volume form is known only when the volume forms are positive. It's a completely open area if the volume forms changes sign. Then nothing is known in this direction. Okay? So this is roughly the situation when we started working on this problem. So this is a joint work with de Coronia and Olivier News. It's a work in progress. So now we are going to describe some of the works that we have been doing in this direction. Now the most important difference between Moses' work and ours lies in the realization of the fact that by solving the constituent equation simultaneously and not separately as what Moses did, we have a much wider flexibility. For example, it enables us to handle a degenerate case, for example, in k is equal to 2 when n is odd, or the higher order differential forms that have not been addressed before. We have also considered the boundary value problem and the question of sharp regularity for the case of closed non-degenerate two forms in even dimensions. So this is what we have considered. Non-degenerate case, there is the boundary value problem and the question of sharp regularity for the case of closed non-degenerate two forms in even dimension, and the degenerate case is k is equal to 2 when n is odd, or k is equal to n minus 1, the intermediate form. What is most difficult is the intermediate case, that is k is greater than or equal to 3 and less than or equal to n minus 2, where the things are far from being complete. So what we're going to do now, we're going to mention two results from each of this section, And if we have time, then we are going to give you a brief idea of the proof. Okay, so what we do is we start with a global result in the non-degenerate case. Okay, so let n be an even number, because non-degeneracy can happen only in even dimensions. So evenness of the dimension is required. Let alpha r be an integer, so alpha, r will stand for the degree of regularity, alpha is a whole order exponent, and omega be a bounded smooth domain. Now let AFG be two closed non-degenerate two forms of the regularity CR alpha in the interior and CR plus 1 alpha on the boundary. Then there exists a diffeomorphism of class CR plus 1 alpha, satisfying the pullback equation, and phi is identity of the boundary, if and only if G minus F is orthogonal to the space of harmonic forms with vanishing tangential component. The tangential components of F and G are equal. The Pfaffians corresponding to F and G, they have the same sign. Now these three conditions are natural, are quite easy to check. First condition essentially says that G minus F is exact, which is something that is known from the topology. The second condition, that the tangential components are same, follows from the fact that the phi is identity to the boundary, because since phi is identity to the boundary, phi star G and G has to have the same tangential component, and therefore we have the second condition. Why do we have the third condition? The third condition arises because phi is diffeomorphism of the domain and phi is identity on the boundary. Therefore, the Jacobian has to have the positive sign, and therefore they have to have the same sign. So this is the naturality of these three conditions. What is crucial here is the sufficiency. Now see that now here the situation is far more complex in the case of volume forms, because what we have is a system here. This is a system of n choose 2 equations, and unknowns are phi 1 to phi n. So this is the situation is a lot more complex here, but okay, nevertheless one can okay, we have done that, so it can be done. Now the technique that we have used to prove this result leads to a very curious local result, which we'll state now. So this is the good old Darboux theorem, but with sharp regularity. Now, what is it? So let n be an even integer, and r, okay, the usual stands for the degree of regularity, alpha is the standard whole order exponent, and omega is an open set, and p is an element of omega, and let f be a closed 2 form that is non-degenerate at a point p, hence is non-degenerate in a neighborhood. Therefore, there exists a neighborhood v of p and a diffeomorphism of class CR plus 1 alpha, such that phi star omega is equal to f and phi p is equal to p. But second condition is free. It does something, it's not very deep. In other words, it says that non-degenerate 2 form is locally equivalent to the standard symplectic form, but that is the Darboux theorem. What is more important is look at the regularity of the diffeomorphism, CR plus 1 alpha. And this is something sharp. Now, if you look at the original version Darboux theorem, there are several proofs available. The usual proof that goes via the dimension, induction on the dimension. But then each time you perform the induction, you lose some regularity. So, of course, in geometers, they work in C infinity categories, that therefore there is no regularity to lose. But if you are interested in regularity, that's not a good proof. And then there is a proof due to Moser using flow method. Again, the same thing appears. It produces a solution that is with regularity CR alpha. But this gives us the sharpest possible regularity. And it's our opinion that, okay, this is how Darboux theorem should be quoted. Okay, so these are the two results that I wanted to mention in that non-degenerate case. Now what we are going to do, we are going to go to the degenerate situation, where things are a lot more, immensely more complex, and this is where our technique comes in. This is where, and the only way to handle degenerate case is to try to handle the constituent equations simultaneously and not separately, that what Moser did. Now, there are two recurrent themes in the degenerate situation. The first thing that is important here is there is no improvement in regularity in the degenerate situation. In non-degenerate case, there is an improvement in regularity. In degenerate situation, there is none. And okay, this is something that we don't know, that how does a geometry play in the role how does geometry play the role in the regularity of the solution? This is something we have not been able to understand. But there are two recurrent themes: no improvement in regularity of solution, and the second thing is almost all the available results are local in nature. Although we have been able to prove some global results, but that's rather artificial, and maybe it's a bit too academic in nature. So we are not going to mention those results here. So we are going to mention two results in the degenerate situation. Let us see what those results look like. Okay, and this is something I have to do. The notion of rank of an exterior form. See, the notion of rank of an exterior two form is something that is quite known, because one can identify a two form with a matrix, 2 by 2, an n by n skew symmetric matrix. And in the case of matrix, we have the notion of rank. Therefore, this can be straight away imported to the case of two forms. What is not known, I would say uncommon, is to have the notion of rank of an exterior k form. So this is how we define it. So n, as usual, n stands for the dimension of the space, k is the order of the differential form, and omega is a k form, exterior k form. The refined rank of omega is the dimension of the space of all one forms that can be realized as an interior product of omega with respect to some k minus 1 forms. That is the dimension of the piece of space, all one forms A, such that there exists a B, a k minus 1 form B, such that IB of omega is equal to A. Now this rank has some nice properties. Now let us see that. Rank of T star omega is equal to rank of omega. That means that rank behaves naturally with respect to the pullback equation. Therefore, it's a good notion for us as far as the pullback equation is concerned. When k is equal to 1, rank of omega is 1. That's something natural. Okay, rank of a two form is always even, but what is more interesting is the thing when k for k form, when k greater than or equal to 3, rank of omega can be anything between k to n except k plus 1. You see, it starts from k to n and k plus 1 is missing. And this has some curious applications in pullback equation, as we'll see shortly. Okay, we are now ready for some results in the degenerate case. So we start with again the good old Darboux theorem. Now, okay, this is not okay. So now L will depend on will stand for the rank, and alpha is the Holder exponent. P is an element of the domain omega, and omega L is a standard symplectic form of rank 2L. Okay, this is not the way normally a standard symplectic form is written, but this really doesn't change any discussion. And let F, wait, it doesn't work. Okay. Let F be a closed 2 form of regularity CR alpha, and rank of S is the 2L in neighborhood of P. Now see, we need to give the condition on rank in a neighborhood, because unlike non-degeneracy, this is no longer an open condition. So you have to impose a condition in a neighborhood. Then there exists a neighborhood V of P and a diffeomorphism of class CR alpha such that phi star omega L is equal to F in V and phi P is equal to P. Note the difference. There is no improvement in regularity here. In fact, we have a counter example. We have considered an example which doesn't give us the better regularity. As usual, we don't know what is the geometric reason behind it. Why the degeneracy gives us the loss of regularity. We can tell you the technical difference. What really happens is that the degeneracy gives us an algebraic constraint. So that algebraic constraint rules out the good solutions. This is what happens in the technical at the technical level, but geometric reasons we really don't know. So that's something that still baffles us. Okay, so this is the case of two forms. Now let us look at what happens for higher forms. This is for the higher forms. So K will stand for the order of the differential form, and R is the usual degree of regularity. Alpha is a whole order exponent, and F, G are two closed K forms satisfying rank of F is equal to rank of G is equal to K in a neighborhood of P. See, this is the minimal rank, because we have seen that the rank of a K form can be at least K. Then these two forms are locally equivalent. Via diffeomorphism of class CR alpha, again there is no improvement in regularity here. So this is something highly, again, the same theme keeps coming back. Now this has a curious application. What is that? Now let us put K is equal to n minus 1. Okay? Now we have seen that. Now what are the possible values of an n minus 1 form? It's exactly n minus 1, right? Because it cannot be K plus 1. Rank of a K form cannot be K plus 1 form. Cannot be K plus 1. Therefore, the only possible values of an n minus 1 form is n minus 1. Therefore, we are in this setup. Therefore, we can prove that any closed n minus 1 forms are locally equivalent. Okay? Now, why we are saying that the case of higher forms is far from being complete, the works, because see here we have considered the case of minimal rank. So what happened when the ranks are in case of higher ranks? The trouble is the notion of rank turns out to be a sufficient invariant for the case of two forms. Now look at the Darboux Theorem. Non-degeneracy means there is a condition on rank. For the notion of, for the case of two forms, it is the rank that plays a decisive role in proving whether there exists a diffeomorphism. But the case of higher forms, it turns out that although the notion of rank is an invariant, it is not a sufficient invariant. We have examples where AFG have the same rank, but there is no pullback diffeomorphism. So the question is, what are the other invariants? That's something we don't know. And this is precisely the problem that arises in the context of studying the higher form, the pullback equation for higher order forms. Okay, and another amusing application. Let us see. Okay, this tells you something on the local structure of zero divergence map. So suppose you have a function of the regularity CR alpha, so that f of p is not equal to 0, and the divergence of f is equal to 0 in the neighborhood of p, then up to a change of coordinates, one can always write f as a wedge product of the gradients. Okay, so this is something quite interesting. It tells you something on the local structure on zero divergence maps. So okay, so I have 7 minutes, right? 7. Okay.
15 minutes.
Oh, okay. Good for me. So okay. Now, so these are the four results that I wanted to mention in this talk. Now, what we are going to do is we are going to give you maybe a 5-10 minutes proof of the theorem of the global result. Okay. So I need a chalk. Is it visible? Yeah. Okay. So I don't need it, no. So what we want to solve is this equation, phi star g is equal to f, and phi is identity on the boundary. This is something that we want to solve. So we have g here, f. We want to find the diffeomorphism phi. The first step that we do is we approximate g and f with smooth forms. So what we do is we approximate g with smooth forms g epsilon and f epsilon. Okay, so these are smooth forms. Okay, and let us assume that f g are in CR alpha with the usual hypothesis that it's that G minus F is perpendicular to the space of harmonic two forms of vanishing tangential components. They have the same tangential component, and the Pfaffian they have the same sign. Let's assume those conditions. The first step is we approximate G with smooth form G epsilon, F with F epsilon in the lower order norm. Now this approximation is slightly subtle because we need a precise control on the rate of convergence. And how do we approximate? So normally the way we approximate, we smoothly approximate is through convolution with respect to a smooth function with compact support. But that is not the right way here. A much better way of a smooth approximation is due to a technique due to Nash. What he did is, instead of convolving with a function with compact support, what he convolves with the inverse Fourier transform of a smooth function with compact support. Now this approach has some advantages. It precisely lets you control the rate of convergence. So this is a much better approach. So we have to do that because we need control on the rate of convergence. So let us assume that we can do this. Now what we want to do is we want to solve three equations. Phi star G epsilon is equal to F epsilon. Phi is identity on the boundary. Phi star G epsilon is equal to G. Phi is identity on the boundary. And phi star F epsilon is equal to F, and phi is identity on the boundary. So we have this diagram, GF. So we want to solve this equation between G epsilon and F epsilon. We want to solve this one, and again we want to solve this. Okay? The question is, how do we solve this equation? See, here we can use Moses flow method because G epsilon and F epsilon are smooth. Therefore, the solution that we get is smooth. That's fine with us. So what we do is, we solve here this equation. And we have some solution phi epsilon. Let's say it's a phi epsilon. So this is by Moses flow method. Now how do we solve these two equations? Now here we cannot use Moses flow method because G is of class CR alpha. Therefore the solution that we get is CR alpha, but we are looking for a solution that is of the class CR plus 1 alpha. Same case here. So Moses flow method is not applicable there. And also note that it's enough to solve one of this equation because these two equations are symmetric, essentially. So let us solve this equation. How do we solve this equation? Although we cannot use Moses flow method here, but there is one. We have one added. We have an advantage here, and the advantage is the following: we can take G epsilon as close to G as we like. Because G epsilon is the approximation, is a smooth approximation of G. So by taking epsilon sufficiently small, we can have G epsilon close to G. So that puts us in the right setup to use fixed point method. So what we're going to do is we're going to use some contraction type argument to find a solution of this equation, some fixed point technique. So let us solve this. So say this is a solution, let's call it, say, eta epsilon. This is a fixed point method. And similarly, let's call it psi epsilon. Once we solve these three equations, we claim that we are done. Why? This is because of the structure of the pullback equation. Now let us define this is the composition. Let us define that this way. So what is phi star G? Now pullback is essentially anti-commutative. So when you take the pullback, what happens? Right? Now what is this? eta star g epsilon is equal to g. Therefore, this is nothing but g epsilon. So this is g epsilon. What about this? This is f epsilon. And therefore, this is f. Okay? So, once we solve these two equations, one can solve the pullback equation. So, therefore, the proof, okay, in some sense is complete. Okay? So, just to, before I finish off the talk, let me give you just the theorem. Let me show you how does the fixed point theorem looks like. So it doesn't. This we don't need. Okay, this is just what we showed. Is we approximate GF with G epsilon and F epsilon. The first G epsilon and F epsilon is solved with the Moses flow method. This is the fixed point method, and again is the fixed point method. Then the structure of the pullback equation allows us to solve as the problem that we have been trying to solve. And yeah, this is a fixed point argument. Yeah, you see, so this is the fixed point method. See, there is the reason I wanted to show you is the following. It justifies why we need the added regularity on the boundary. If you look at the fixed point theorem, you see that G is of the class CR alpha, CR plus 1 alpha, and F is CR alpha. So to use the fixed point method, we need added regularity on the G, on the interior. But while combining the Mozart flow method, when you do the approximation, this extra regularity on the interior gets transferred to the boundary only. Okay, and this shows that when F and G are close in some lower order norm, then we can solve the pullback equation. Okay, and once we have this theorem, we use the approximation scheme due to approximation scheme that solves the pullback equation for us. I think I will stop here. Thank you.